Hi class. I wanted to first say a couple things about the website. I sent you an email tonight kind of describing how to do things. I'm a little worried because a lot of people keep asking me where the problems are and what problems they're supposed to be doing. My webpage is very accessible. All you have to do is type Nerz-Stormes, Google Nerz-Stormes, and it's the first thing that'll come up. It's hard to miss, so just bookmark it. That front page, which is very colorful, has a lot of stuff on it, I admit it, and there's a lot of stuff on my website. However, there are certain places that are more important than others for you. First of all, at the very top of the web page, when you're on the page that has my picture and has the picture of the tulips on it, the top place where it says where it says chat room, that's where you go to the chat room. You just click on that and you're in the chat room. The third button down has the topics for the course. This is the thing I think that's causing the most trouble. The course has a very definite organization. You may not know what that organization is or may not understand it, but there is an organization. It's not an organization based on a textbook, and I think that's where the problem comes in. It's my own pedagogy, and it's based on 25 years of experience, and it works pretty well for most students. In other words, if I teach students language really well at the beginning of the course, more so than it's done in the textbook, they usually do better in organic chemistry because, believe it or not, you haven't even seen what organic chemistry is yet. Like, you don't even know what it is yet. Maybe you do, but I think we have a long way to go. So that third button, just click on it, then click on topics, and then and I've shown this in class a few times, it says exactly what we're doing. I mean, it's not that complicated. And I wrote down every section that we're doing, every problem, and all you have to do, we're in Unit 2 now, we're toward the end of Unit 2, we're doing optical isomers right now. If you just go to the right, there's a blue URL, I guess you would call it, or an embedded URL. You just click on that, and it gives all the problems you're supposed to be doing. So right now, we are in optical isomers. We're probably about a day behind schedule, but that's not unusual at this point. We'll be doing that all through the week. You shouldn't be upset if it's not totally making sense to you. We're going to really try to make the office hours move along this week and be very focused on the work in the course, okay? So if you're waiting and you have a question to ask, just like pop your head in and I'll get you in there to ask questions about the material in the course. All right, so right now we're in optical isomers, which is Chapter 6. Chapter 6 is in your textbook. If you click, it'll show you which problems that I recommend. Generally speaking, if you do just about every other problem, you'll be fine. There's so many problems in that book, it's not funny. Start using the book if you haven't used it yet. You don't have to. Some people manage without it, but I think it's a good idea. It also says Stereochemical Web Book. On the front of my web page, I just talked about the third button. On the bottom of the page are all the web books. These are supplemental materials that I wrote specifically for the course because I'm trying to write my own textbook, actually. But I'm trying to write a web book. But the Stereochemical Web Book is right down there. It has all kinds of videos embedded in it. There's also the spectroscopy as imaging. Now, the problem with that is they changed one of the main links in it, and we have to change that. But I sent that to you tonight, and that's going to be changed really soon. So again, chat room at top, third button gives you all the topics. All the webbooks are on the bottom of that front page. You really just have to work from that front page. Just bookmark it. And then the last button on the page will get you to all the answer keys that you need. Now, a lot of this material is also on Blackboard. If you go into the Blackboard course materials, you will find the topics page. You will find the answer keys to the textbook. You will find a lot of videos. You will find a link to my YouTube site. You'll find lots of stuff there, including these new web books. So try to just familiarize yourself with that and kind of give the organization a chance because it does have some merit. Maybe it's not the way you want it to be. You want it to just follow along a chapter line in a textbook. But I developed it so that students would learn the material better because a lot of people really struggle with organic chemistry. Organic chemistry is not an easy course. And I really want everybody to succeed in the course. That's very, very important to me. And that's the purpose behind that organization. But look at the organization and give the organization a chance. And again, if you want to know where we are, we're in chapter 6. I say it every day in class. Every day in class I write where we are and what we're doing. As far as last week goes and the confusion about the quiz for the undergraduates, I'm really sorry about that. I was really sick for a week. It's not a good excuse, I suppose, but I really had some just problems at night where I couldn't do work. I'm doing better, so hopefully things will go nice and smoothly this week. All right. So anyway, I just want you to get used to that website. The other thing I wanted to say, just generally, and I don't want to spend class time on it, is that if a question is way too physical, like it's really a physics question, or it's way too biological, it probably doesn't belong in class. I mean, it's okay to come and discuss it, but it probably doesn't belong in class, because a lot of people have not had physics, and a lot of people have not had biology, and a lot of people get really thrown off when the questions are way outside the range of organic chemistry. Chemistry is the central science, right? And we kind of walk a fine line, you know, between physics and biology. And we know some biology, we know some physics, but the truth is we use physics to solve our chemical problems that we apply to biology. That's kind of how it is. And if you went into anybody's field, you would discover, you know, how they see the world, okay? And we're trying to look at the world as organic chemists. So in class, we're going to be organic chemists. If you have other questions, you can ask me. I will be honest with you. If it's a question that's like kind of a heavy-duty physics question and I don't know the answer, I will tell you. On the other hand, I will also try to look it up. I always try to review things, refresh my memory, go back, you know, read things again. I'm all into that, but I'm just telling you that. Classroom time, we're doing organic chemistry. And it's going to take a while for you to even to understand what organic chemistry is. Like, what do organic chemists think about? They're usually thinking about reactions and mechanisms, and, you know, how reactions occur and how you analyze molecules and things like that. It's kind of like it's a molecular perspective, which is a little different. Okay, so before I sign off here, I wanted to do a little bit of stereochemistry because people are already asking about how to do it, even though we'll do it tomorrow in class. What's my time right now?
7 minutes.
Okay, good. So I just wanted to do a little bit of this and show you how this weaves in with what you learned about Z and E stereochemistry. And by the way, I hope what I just said it didn't come off wrong or anything. I really do not like to stifle curiosity. It's just that there are 120 people in the class, and we do have to progress every day. Like, it's important. We have to progress in organic chemistry every day, and that's very, very important. So anyway, as far as the stereochemistry goes, I kind of left you like hanging in the midair on Friday, and I just wanted to show you how you actually solve the problem. So if I draw an amino acid, I'll draw a different one than the one we had in class. And what we're going to go over tomorrow, we're going to talk a little bit about how to draw structures in different three-dimensional manners. Okay, that's a benzene ring. So this is going to be phenylalanine. Okay, so this is phenylalanine. This is one of the amino acids that you find in aspartame, which is in an artificial sweetener. We were talking about that on Friday. So this is an amino acid, and it's chiral. Okay, how do we know it's chiral? It has one and only one asymmetric carbon. And remember, one of the important things is to learn all the definitions. What is an asymmetric carbon? An asymmetric carbon is a carbon with 4 different groups. Okay? So this is one way you could represent a tetrahedron in 3 dimensions. It's with 2 bonds in the plane and 2 out. I purposely did something a little different from what I drew in class yesterday. Okay? So how would you go about this? There's a lot of little tricks that you can do. So I'm going to draw another molecule. So say I drew this. We want to establish what the relationships are between these two. Of course, I just drew something that was kind of difficult, but that's okay. So I'm going to draw. This is another way you could represent a tetrahedron. Okay, and I'm going to show another one. Another tetrahedron, and we're going to establish what the relationships are between all these molecules. I wish I had my models home with me, but I don't. So I'm just drawing all different perspectives on phenylalanine, but the truth is there's two phenylalanines. There's two orientations. And I was showing you that idea last Friday with models, okay? So what I said to you on Friday was you have to assign priorities. So you have to assign priorities 1 through 4. Okay, instead of 1 and 2 and 1 and 2, 1 through 4. Then what you do is you put the number 4 group so it is pointing away. Now the way the textbook presents this, it really involves molecular manipulation. You have to manipulate the molecules. Okay, and then third, what you do is you trace a circle from 1 to 2 to 3, okay? If that circle is clockwise, it's R. If it's counterclockwise, and this stands for rectus, the word rectus, and if it's counterclockwise, I don't know if you can see that, it's S, which stands for the word sinister. Okay, so all you left-handed people out there are sinister. Anyway, so this is kind of like the basic deal. You assign priorities using CIP, which you've already learned how to use. And I know some people are kind of freaking out about this, but it'll get better. All right, and so if I assign priorities, they're the same for all these molecules. So the question is, are these molecules the same molecule or are they different molecules? So the hydrogen is obviously the lowest priority. The nitrogen is the highest priority. Okay, now these two tie at the first level, C versus C, but this really has, because it's a carboxylate group, and you better go over your functional groups again, because this is a carboxylate group, it has 3 oxygens attached to it. This has 2 hydrogens and a carbon attached to it, so this is OOO, and this is HHC. This is higher priority. So this is 1, 2, 3. It's going to be the same for all these molecules. 1, 2, 3, 4. 1. This is the same way we did priorities for double bonds. 2, 3, 4. Okay? So, I will tell you right now, this one's the easiest to do. The reason this one's the easiest to do is it follows those rules beautifully. It says, put number 4 group so it is pointing away. Trace a circle from 1 to 2 to 3. Now, the reason this is a great looking model or molecule is that number 4 is going away from you. Okay? Why is it going away? Because it's a hash. Wedges are coming out towards you. Hashes are going away from you. So, when I trace the circle from 1 to 2 to 3 and number 4 is going away from me, it's clockwise. So this is R phenylalanine. Okay? Now, what are these others? Again, there are 2 phenylalanines that are mirror images of each other because this molecule is chiral. Okay? This one is a problem. I'm going to do this one last. Okay? This one you can use a little trick. There's lots of little tricks you can use with this, but the main trick I tell people is, I'm almost done. If number 4 is coming towards you, in other words, if you have an inconvenient looking structure, all you have to do is trace the circle, and a lot of people don't believe in this at first, and then reverse the designation. Now, I'm going to go over this again tomorrow. Okay, this is not going to be skipped in class, but the more you see this, the more you'll believe in it. So the thing is, on this one, I'm going to trace a circle from 1 to 2 to 3. It looks clockwise, but number 4 is a wedge, which means it's going the wrong way. Now, you think about this. If I was on the other side of the board, I would actually get the reverse designation. I'm going to demonstrate that in class. So what I do is I trace it. It looks like it's R, but it's really S, phenylalanine. There I'm using a little trick. Now, why do I teach people these tricks? Because some people can't see things in 3D. Students are really good at doing this. They have no problem doing this.
That's 15.
Okay. And the other thing is people make mistakes when they manipulate molecules. Now what the text would tell you is to take this molecule and turn it in space and then trace the circle, and it would indeed be S. Now this one's the real problem child. And the reason this is the problem child is because number 4 is in the plane of the board. Now for you guys in the beginning, it wouldn't be bad to build a model and move it so number 4 is in the back. What I always did, I always tell students I didn't have models. I just never bought them when I was in college. I guess I just didn't want to buy models. Or maybe we didn't have them back in the olden days. I don't know. In the days of the dinosaurs. But you'll see, but what I do with these, and I'm going to show you this in class, is that I tend to, like, instead of move the molecule, I move myself. And what I do is I put myself, like, over here. And I think about the spatial aspects of my arms and legs, okay? So in my little book, I call this stereochemistry woman. Some people hate stereochemistry woman. Okay, but anyway, and stereochemistry woman, her left arm in this picture would be a wedge. Her right arm is a hash. Same thing with her feet. So the thing is, if I was standing over here, number 1 would be down by my feet, number 2 would be back here, and number 3 would be over here. And when I trace the circle, it's S. So this is S phenylalanine. Now if you reverse this and look back over it, I had 2 molecules that were S and I had one that was R. S and R are enantiomers, but the 2 S molecules are exactly the same molecule, and you could prove that using models. Okay, so I'll see you in class tomorrow.